Okay, so today we're going to talk about z-scores. Z-scores are awesome. Okay, so let's imagine things. Imagine we have two students that are applying to become psych majors. Before this semester started, we actually had a whole bunch of students that were applying to be psych majors. And there's some committee that determines like who gets to be a psych major and who doesn't, because there are limited numbers required by Yoke who can be psych majors, right? So imagine that the psychology department can only accept one of them, all right? So you have two people applying, the psychology department is going to accept one. Now imagine that the department will base its decision on the student's performance in intro psych. That's reasonable. How well they do in intro psych should suggest how good of a psych student they could be. There are other things that they should probably look at too, but let's just imagine that that's the only thing they're concerned about. Now, imagine that they had different teachers for intro to psych. Okay, so some people had me, some people had Sammy, some people might have had Alif, but the two students that we're talking about, they had different teachers. So we had the student one, they got a percentage in the course of 87. All right, so they got an 87 in their class. Student 2, who took a different course, got an 84. So the question now is, which student should the department accept? It depends. It depends. Is that right? Yes, that's exactly right. So if you were thinking student 1, duh, well, that's reasonable to think, but it actually depends. So, what I told you was, what if I told you that the mean percentages for each class were as follows? So, in class 1, the mean percentage was an 87. In class 2, the mean percentage was an 81. Now do we know who we should accept? We should accept the second one. Why? So we said that what did we say student 1's percentage was? 87, right? And student 2? 84. All right, so we know what the students got, and now we know the means for the classes that they were in, right? So you said that we should accept the second student. Why?
Because she's over average.
Huh, so this student actually did better than the average. The student did better than the mean in that class, right? This student, how did they do? They got the mean. They got the mean score, right? So student 1's score was 87, that was the mean. Student 2's score was of 84, was actually above the mean for that class.
But why should we care?
Why should we care?
Like about this class can be more challenging than the other class. This class can be much more the instructors are different, so it doesn't mean, you know.
So part of what you're saying is right up. So classes differ, right? Some classes, the way some teachers teach it, make it easy. Some classes, when the teacher wants to use R, makes it more difficult, right? So if you have a class where it's easier, then the scores on average should be higher than the class in which it's difficult, right? But can we make any assumptions about how the students are in those classes? Do we expect that the abilities of the students in those classes are going to differ?
How can we know that? And we are not in school, we are not in class, so just we know their points, their successes.
So if we were giving both of the classes in the same semester, like maybe the smart students, they might say, oh yeah, I want a really challenging class, right? So I'll take the harder one. And maybe the students that were a little bit scarier, weren't as confident, whatever, they decide to take the easier one. Okay? But the way it's set up, at least here right now, is you have one statistics class in one semester, you get your shot and that's it, right? So is there a reason to expect that like the students in statistics this semester are different than the students in statistics last year? We'd expect, I mean, it's sort of like, it's not exactly a random sample, but it's similar to a random sample, right? We should expect some really strong and motivated students in both classes. We should expect some sort of weak and unmotivated students in both classes, right? So the difficulty might push those means up or down, but if the underlying students are the same in both, then we can do this type of comparison and look at how one student does compared to the mean student in that class, right? The mean student's ability should be the same in both classes, right? Does that make sense, Alan? All right, so let's take the student two. All right, cool. Now, what if I said something different? What if I said that the mean for both classes was 75%? Which student should we take?
First one.
Take the first one, right? So 87 and 84, these are both over the mean, but 87 is more percentage points over the mean, right? Well, that makes a lot of sense. Take student one, go. Not so fast. Not so fast. Why not?
The questions, some questions are the questions are same.
Uh-huh.
No problem, but the questions are.
So, we said that if the class was more difficult, like if the questions were harder, this would make the class more difficult, right? This should push the mean up or down, depending on the difficulty. What else is there that we've talked about so far besides the mean?
Number of students.
Number of students, okay, we talked about sample size. What else?
Variability.
Variability. There might be different variability in the classes. So, have you heard about classes where like almost everybody gets an A?
Yeah.
No?
Almost.
Yeah.
Almost.
Yeah.
I forget the name for these classes. There's a particular name. And like, if you want to boost your GPA or you don't want to work hard in the class, take this class. Because you get an A, right? Which suggests that the variability, if almost everyone is getting an A, the variability is really low. Now, there might be other classes where not everyone is getting an A, or most people aren't getting an A. So we can think not just about what the average score is, but we can think about how spread out the scores are, right? It's possible that there's differences in the variability of the two classes that's not related to the variability in the students, but is related to the variability in how the teacher instructs, the types of questions that they use. So it's possible that differences in variability could matter. So in order to figure out why this does matter, let's make the example really, really simple. So let's say that the mean was 75 in both classes, and let's say that both students scored an 87 in both classes, okay? So the means are the same, the scores are the same. Let's see how variability is going to affect our interpretations of the scores. Let's see if we are going to come up with different answers for the different students. Without taking variability into account, they look exactly the same. The means were the same, their scores were the same, they're basically the same person. Let's just flip a coin, right? So let's see if variability does affect things. So now imagine that the first class, you have a mean, what did I say it was, 75? Is that right? So notice that the mode is going to be at 75. The mean is also at 75. And now we have a standard deviation of 8. Now, a standard deviation of 8 tells us something about how spread out the scores are, right? So, we said our student had a score of 87, is that right? So they have a score of 87, so that's marking a score of 87. So our student is there. Now, the question is, how well did this student do? Right, this is our student score. How well did they do?
Not good.
Not good.
Not very good.
Not very good. Does anyone else have anything different? I have a different interpretation. I think they did good. They did well. They scored better than the mean. That's good. You have really high standards, so I applaud you. But this is better than the mean. How much better than the mean is it when you take into account the spread? If we want to think about this a little differently, like, how many people have that score or more? A lot? A few? None? Few. Few students have scores higher than that. So our student is above average, but they're not like the best in the class, right? So if I calculated the probability of picking a student at random that does better, the probability that is the sum of this area in here. So this is like the binomial. Remember how we were adding up probabilities? So we're sort of doing the same thing here. I'm not going to talk about how you calculate this today. We'll do that tomorrow or Friday. Anyway, so the probability of getting a student at random that does better than this is 0.067. So that means like almost 7% of the students did better than this one. Does that make sense? Now, imagine if instead of having a standard deviation of 8, we had a standard deviation of 4. What's going to happen to the distribution? The standard deviation index is how spread out scores are around the mean, right? So if we have a smaller standard deviation, everyone look at seatbelt, do it again. It's going to pull those scores in more tightly around the mean. Whoa, look. So this was 8 with the standard deviation of 4 and exactly the same mean. It pulls things in quite a bit. If you look at this axis, this is also changing as well. So the scores are getting tighter to the mean, and this peak is actually getting a bit higher. So that's going from almost 0.05 to almost 0.1. Right? Why? Well, because you're packing those scores in, so that's going to go up higher. Right? All right. So now how did this student do? This student did really, really well. Really well. Right? Again, they're above average. They're above the mean. But there are very few students that did better than them. So if we took the probability of picking a student at random that would do better, the probability is almost 0.001. This means that, like, he's in the 99.9th percentile, right? So only 0.1% of students are doing better. It means they're at like the top, he or she, right? Wow, well, now we see that the variability, or the variance or the standard deviation is affecting our interpretations of these scores. Does everyone see that? Let's take a very different example. Who has friends? Everyone, I hope so. When you get around with your friends, do you talk about like stuff that you do and things that you enjoy? Talk about things that you did good at or well at. Sorry, my grammar not so goodly, my grammar. Anyway, so you might tell your student like, oh, well, I got a 97 on that test. And they're like, oh, whatever, I got a 98 on this other test, right? So who does better? Now, that's sort of similar to what we were talking about before. So let's take a very different example. When I was in college, we wouldn't talk about like test scores when we were trying to like determine who was the coolest. We'd talk about other things like, dude, that was the stinkiest fart ever, yeah. Or I can make the loudest burp. or I can hold my breath longer, I can do this, I can run faster, you know, whatever. So imagine that you have two friends that are bragging about their talents. And one says like, dude, I can hold my breath for a minute and a half. Right? They hold their breath for a minute and a half. Another person's like, yeah, that's pretty cool. You know, that's better than me. But I can eat 20 eggs in 6 minutes. Watch. How many of you guys have seen Cool Hand Luke? Has anyone seen Cool Hand Luke? Watch it. Guy eats 60 eggs in 60 minutes. It's a lot of eggs. All right, so he eats 20 eggs in 6 minutes. Another guy's like, oh yeah, I can do that. And then he tries and he doesn't do as well. He's like, well, you know, that's pretty sweet. 20 eggs in 6 minutes. Now, which student is more impressive? Which friend is like, you know, can do something more amazing than the other? Which accomplishment is more impressive?
You have to look at the other.
The other what? We have to look at the other what?
You have to look at the variance of the same activity if the others are doing it.
Yeah, we need to look at the variability of number of eggs that people can eat in 6 minutes. We need to look at the variability of, you know, how long people can hold their breath. Does that make sense? What else do we need besides the variability?
The mean.
We need the mean. We need the mean, right? Because if we just know the variability, but we don't know what the mean is, we don't know if they're better than average or worse than average or what. So we need the mean and some measure of variability. What we need to do is some way to standardize the scores, right? That are going to allow us to compare different types of scores directly. So let's incorporate the mean first. So earlier we were able to tell which student was better when one was above the mean and the other was below the mean, right? Or actually we had one above and one at. But if you have one above and one below, then you know which one is doing better, right? So how can we incorporate the mean? How can we determine, create some score that tells us whether the student is above or below the mean? So we have some score, we have a mean, we want to know if the score is above or below that mean. What can we do? I mean, we could just look, right? Let's make a formula that will give us the answer. So, I ate 20 eggs, and the mean is 18 eggs. Am I better or worse than the mean?
Better.
I'm better than the mean. If you combine the mean and my score in some way, is there some way that like I can get an indication immediately by looking at the resulting answer? I can take a difference. Ooh, I can take a deviation score, right? So if I take my score and I subtract the mean, if my score is above the mean, I'll have a positive answer. If my score is beneath the mean, I'll have a negative answer, right? If my score is at the mean, I'll have 0. That's exactly right. So let's subtract the mean from the scores in question. This is just the deviation score, which we talked about last class. So if the deviation score for eating eggs is positive and the deviation score for holding breath is negative, then we know our answer, right? So, how did I decide the mean? Why would I use the mean? Say what? I didn't just make it up. So why would I subtract the mean from that score? I mean, I could subtract other things from that score, right? I could subtract the mode. I could subtract the median. I could subtract the standard deviation. The mean is the balance point. The mean is the balance point. It has a special property, right? About being the balance point. And this will allow us to do some fun stuff. But we don't know the mean. We might know the mean. You could look up, you know, in like eating contests. Like, so they have records of this person ate this many hot dogs, this person ate that many eggs, so they have records for this type of stuff, okay?
And
So you're absolutely right. If we don't have the mean, we're going to be in big trouble. But for right now, we're going to assume that we have the mean. This is not always the case, and we'll see what? Not next class. After the test, we'll see how we can estimate the mean if we don't have it. And then we'll be able to do this anyway. Okay? But this is a good point that she's making. If we don't know what the mean is, we're going to be in trouble. So for the examples that I give you, I will tell you what the mean is. All right. Now, what if they're both positive? What if the deviation scores are both positive? Then what do I need to do?
Which one is more?
I need to see which one is farther away from the mean in terms of how spread out scores are, in terms of how variable scores are. So that means I need to incorporate a measure of spread. And I'm going to use the standard deviation. I could use range, I could use the maximum, I could use other things. Maximum, that would be a really weird thing to sort of take account for. Variance would make a little bit more sense. But we're going to use the standard deviation because we're getting a deviation score. So if we have a deviation score, the standard deviation is a standard deviation. And if we divide a deviation by the standard deviation, we get like a standard score. So our reasoning behind picking these things has some logic behind it. Okay, so earlier we were able to tell which student was better by comparing their scores to the variability of the distribution, right? So let's compare their deviation scores to the variability. So how do we do this with standard deviation? So we have the deviation score, right? That's just the score minus the mean. How can we account for the variability?
We get square.
We could square the deviation score. Now that would give us a squared deviation score, but that's not going to tell us where that score fell in terms of variability, in terms of spread from the mean. That will just square it. We want to do something, just like before, to incorporate mu, to incorporate the mean, we did some function with it. For the mean, we subtracted that from the score.
We add.
So maybe we could add the standard deviation to our scores. What would that do? Imagine that we added the standard deviations to our scores. So imagine I had our students here, and the deviation scores, let's say both of the classes had means of 75, right? So if that's the case, then our deviations, what will our deviations be? Well, here it will be 12, here it will be 9, right? Now, let's say I am going to now add the standard deviation. So I need to know what the standard deviation is, right? I mean, if we don't have it, we can't do it. So let's say that the standard deviation for both of these, or not for both of these, let's say for this one it's 10. So the standard deviation for, since we're talking about the population of all the students in this class, we can represent it with sigma. Let's say this is 10, and let's say that this is, I don't know, 12. Now, if we're going to add the deviations to the standard deviations, we're going to get something like 24 and 19, right? So which one is more deviant if we were to do this? The first one? So this has a bigger score total, right? This has a smaller score. What if I change things a little bit? Let's say, what was that before? It was 12? Say made this 10. Okay? Now we have 22 and, well, 19.
Same.
This one is still bigger, right?
Yeah.
But let's think about this for a minute. Now, we want to compare their score to the variability of the distribution, right? So we have an index of the variability of the distribution here, the standard deviation, right? Now, this 12, is this more than one standard deviation, less than one standard deviation, or what? While you guys are thinking about that, I'm going to reset the camera. Thank you. All right, so which one is farther away from the mean in terms of the standard deviations? 22? Why? Well, let's take a look. This is actually smaller than this, right? That means that it's less than a standard deviation away. This is bigger than this, right? Which means that it's more than a standard deviation away. Now, there's a problem with this, though. Let me do one more. Let's do a really crazy one. If we just look to see what the biggest one is, what answer are we going to come up with? Well, this is still the biggest one, right? But this isn't even close to being one standard deviation away, right? This, on the other hand, is 9 standard deviations away, right? So if the standard deviation of 1, this means that the scores are very, very tightly packed around the mean, which I said is 75. So that means that 9 standard deviations away, this is quite a bit a ways away from where a lot of that data is. If, on the other hand, we have a mean of 75 and a standard deviation of 100, that means the stuff is spread all over the place. So, like, we can keep running. Hello out there, right? And so, comparatively, a score of 87, it's in the middle of that spread, comparatively, right?
Do we need to divide?
Do we need to divide?
Divide deviation with sigma or something?
Maybe what we don't want to do is add. Maybe what we want to do is divide. You're absolutely right. Let's divide the deviation scores by the standard deviation. This will give us the standard score. This is a good way to find out how far away something is from the mean. This is also known as a z-score. This standard score is a z-score. Now let's take a closer look at what this does. Now imagine we're back to our eating eggs. So we need the population mean and the standard deviation to do this. If we don't have it, we can't do it. Unless we can estimate it, which we'll learn how to do later. But for right now, let's assume that we know these things. So we know that when people are told you have 6 minutes to eat eggs, eat as many as you can, go, that the mean is that they eat 12 eggs in 6 minutes, okay? And the standard deviation is 4 eggs in 6 minutes, okay? So how do we compute the z-score? How many eggs did I say the person ate? Said 20, right? So this person can eat 20 eggs. So what's the z-score for that?
20 minus 12.
So 20 minus 12, this is the deviation score, right?
And 4.
And then over 4. So 20 minus 12, that equals 8 over 4. This equals 2, right? So boom, there we have it. Now, I want you to notice something. We said 20 minus 12 divided by 4. That's not actually what we were doing. This is 20 eggs minus 12 eggs in 6 minutes. So the deviation is 8 eggs in 6 minutes, right?
So,
The standard deviation here is 4 eggs in 6 minutes. Now, what happens if you divide 8 eggs in 6 minutes by 4 eggs in 6 minutes? It's not 2 eggs in 6 minutes.
2 eggs. The minutes will cancel out.
1 point something.
The minutes will cancel out and the eggs will too. Right?
People, the number of people who are able,
Huh?
the number of people who are able to do the same thing.
No, this is just math, right? So let's say 2 times 5 minutes equals what?
10 minutes.
Okay, let's do something simpler. Let's do something really, really simple. Let's say we have some office that a student is going to stay in. And the length of the office is 2 meters. And the width equals 2 meters. Right? What's the area? 4 meters squared, right? We take the length, we multiply it by the width, right? So 2 meters times 2 meters equals 4, right? That's 2 times 2, and the meters squared, right? So if I say 2 times 2 meters, what does that equal? It's just 4 meters, right? So if I were to divide, let's say I'm going to divide both sides by 2 meters, right? So 2 meters, 2 meters, what happens? It's just going to be 2. This 2 meters is going to cancel out, right? So those meters are canceling out. Boom, we're left with 2. So this is not 2 eggs in 6 minutes. It's just 2. So we found that the z-score, it gives us a unitless measure. Unitless. It doesn't have units with it. It doesn't have eggs. It doesn't have minutes. It doesn't have, it's just 2. Right? What will we do with this? Well, this is really cool. Because it's unitless, we can compare it with other unitless measures. Right? I mean, how do you compare 2 eggs to 5 apples? Right? They say you can't compare apples to oranges. Well, you can compare apples to oranges if you standardize them. If you get rid of the apples part and you get rid of the oranges part, which you can do with the z-score. So our z-score is 2 for the egg eater. Now, this tells us how many standard deviations a score falls away from the mean. This is an index of extremity, right? It tells us how extreme a score is in terms of the mean and the standard deviation. All right? Cool. It also tells us the direction of the extremity. So, because the z-score is just a function of the deviation, when the deviation is positive, the z-score will be positive. When the deviation score is negative, the z-score will be negative. So by quickly looking at the sign of the z-score, we can tell whether something is above or below the mean. Then by looking at the absolute value of the z-score, we can see how many standard deviations away from the mean it is. Right? So by looking at both pieces together, we see how many standard deviations in some direction a score is away from the mean?
If it was minus 2, what does that mean?
If it was -2, what does that mean?
Below the mean.
It's below the mean because of the minus sign. Now what about the 2 part?
What's his name?
Doesn't matter. It doesn't even matter what the mean is. It is 2 somethings below. What are those somethings?
Score.
A score of -2 would tell you that that score fell 2 standard deviations below the mean. A score of 1.5 tells you that it was 1.5 standard deviations above the mean. A score of -0.333 repeating tells you that it's 1/3 of a standard deviation beneath the mean. Okay? All right, so if it's above, z will equal 0. If it's equal to 0, I'm sorry, if it's above, z will be greater than 0. If it's equal to the mean, z will equal 0. And if it's below the mean, z will be less than 0. Okay, so now let's compare eating eggs with holding breath. So, eating eggs, 12 eggs in 6 minutes, knowing what the population mean and standard deviation were, which I gave you guys, we came up with a z-score of 2. Now, let's look at holding breath for 1.5 minutes. Well, how do we calculate the z-score for this? If we're going to calculate the z-score for holding breath, we need things, right? We need the mean, we need the standard deviation, and we have our score. So imagine that the mean and standard deviation for the population are as follows. So the mean is 81 seconds. The standard deviation is 12 seconds. And what's the score for this person? 90 seconds, right? A minute and a half is 90 seconds. So how do we do it? 90 seconds minus 81 seconds all over 12 seconds. Well, this is 9 seconds over 12 seconds. The seconds are going to cancel out, and we'll be left with 3/4, 0.75. So, our breath holder also did better than the mean, but comparatively, which one did more extreme, is more awesome? The first one was 2 standard deviations away from the mean. The second one was only 0.75 standard deviations away from the mean, right? So in terms of standard deviations, the first one was more away from the mean. Do you have a question?
No, I did.
Awesome. I want you to get it. So eating 12 eggs in 6 minutes is way more impressive than this, if those means and standard deviations really are what I said they were. I made them up. But later in this class, we use a real example that isn't made up. Actually, it's sort of made up, but it's, well, we'll get there when we get there. Okay, so back to our question. We have our 2 students, right? Our first student, they had an 87%. Now, they came from a class that had a mean of 78%, and the class standard deviation was 6%. So, what's their z-score? Well, let's do it, because some people aren't just going to be able to give the answer. 87 minus 78 divided by 6. So this is 87 minus 78? 9. 6. 3 over 2? 1.5. 1 point something. 1.5. Right? So that student has a z-score of 1.5, which means that they fell 1.5 standard deviations above the mean.
Yeah.
Okay? Now, the second student, I said that they had a percent of 84 in the original example, right? So they have the percent of 84. Now let's say their class had a mean of 72. And, I'm sorry, 72%. And the class standard deviation for that class was 9%. So, what do we do? How do we get it? 84, 72. So 8, 12, 9. So this is 4/3.
1.3.
Like that, right? 1/3. All right. Did I get it wrong?
No?
All right. So which student should the psychology department pick? First one. Not because the percent was higher, right? Because the raw percent doesn't matter. It's only that percent in relationship to the mean and the variability that's going to allow us to determine how well or how poorly someone did in a situation like this, right? So we're going to pick the top student. Here's a different question. What if both classes had the same standard deviation? Second one, why? The upper one is higher. I'm not sure I understood. Now, instead, let's look at this last term here, okay? 9/6, 12/9. If these are both the same thing, we would have something like 9/whatever it is, right? Versus 6/whatever that thing is. I'm sorry, 12. 12, yes. I'm fixated on the 6. 12. This one is going to be more. No matter what this is. If they're the same, then this student is the better student, even though they had a lower raw score. Does that make sense? So we need to account for the mean and the variability. Okay, so what's the probability of observing a student with a z-score of 2 or higher? So we talked about, okay, so we had a student that has a z-score of this, or we had a student with a z-score of that. When we were talking about the binomial, we were talking about number of successes, right? What's the probability that we would get this many or more successes? So this is a similar type of question to what we were doing with the binomial. This is a p-value, right? This is a one-tailed p-value because I said 2 or higher instead of as or more extreme than 2, right? If I said as or more extreme than 2, that would be two-tailed. So this is a one-tailed p-value, and this is going to depend on the distribution. When we were doing the binomial, we talked about a binomial distribution. Now we're going to talk about a different type of distribution. Let's say that the distribution was normal. On Monday, we are going to talk a lot about normal distributions. All right, so earlier we talked about the binomial, so let's review what we did for the binomial and see if we can apply that to the normal. So with the binomial, we said that to calculate probabilities, we needed 2 pieces of information, right? The probability mass function, we needed to tell it the sample size, and we needed to tell it, what else? Probability of success. Good. Now to get the p-value, we just add up all of those probabilities for some number of successes or more, or some number of successes as or more extreme than that, depending on the tails. And what was considered as or more extreme just depended on the direction of H0. But basically, we had some function that was able to calculate probabilities. And then we just summed up the right probabilities, right? So now on to the normal. To calculate probabilities, again, we're going to need 2 pieces of information. What 2 pieces of information do you think we're going to need, given the things that I've talked about today thus far? We're going to need some index of variability and the mean. What index of variability? Sigma, which is the standard deviation. So to calculate the probabilities for a normal distribution, we need to know the mean. We need to know the standard deviation. Now, to get the p-value, then we're just going to add up probability masses, just like we did for the binomial distribution, and which ones we add up depends on our null hypothesis. Okay, so let's take a look at what normal probability distributions look like. We talked about normal probability distributions a few classes ago. Does anyone remember what I said they look like? The normal distribution, the mean, the median, and the mode, they all equal the same thing. So it's unimodal and it's symmetrical. Yeah. It looks something like this. So with a mean of 100 and a standard deviation of 15, we have a normal distribution that looks like that. So it's a bell-shaped curve, it's symmetrical and unimodal. Symmetrical word? That might just be symmetric. Symmetric and unimodal. All right, so that's with a mean of 100 and a standard deviation of 15. How about for a mean of 25 and a standard deviation of 4? What's going to happen? She's going like this. With a standard deviation of 4, things are going to be more tightly compact, right? So it's going to be more tightly compact, which means that the height of this is also going to be a bit taller, right? Because you had originally mass spread out over a large area, and now you're pushing all that mass into a smaller area. Okay, so the mean should now change to 25. Now I have scaled this, so that way the scale looks the same, but notice that the mean has changed. So it went from 100, now it's 25. Let's look at the height. We said that the height should change. So before, with 100, it went up to, let's see, 0.01, 0.015. So this is 0.025, a little bit above that. So when we go to our new mean and standard deviation, that should increase. Well, now instead of 0.025, it's like 0.1. So yeah, it got packed around. I'm just stretching that out, pushing it down so you can see that the shape is the same, right? It's basically the same shape if you look at it with the right scale. So same basic shape, it's just a little narrower and taller for smaller standard deviations. This is easier to see if you plot them with that same axis. Okay, now what if we standardize a normal probability distribution? How do we do that? How do we standardize a score? A standardized score is another word for a z-score. How do we get a z-score? Standard deviation what? Mean, standard, okay, what's the function? Score minus mean, all that divided by standard deviation. Now, we have scores here, 10, 11, 10.5, 10.11, 25, lots and lots of different scores. So what we could do to standardize it is just standardize each of the scores. We're going to divide basically everything there by the standard deviation after we've subtracted the mean from it. Is the z-score 0 here? I'm not sure. I don't follow the question. Well, the z-score, like, there's no z-score for the distribution, just like there's no score for the distribution. This is a distribution of scores, right? So if we have a distribution of scores and we want to standardize those scores, and we want to standardize the distribution, we just standardize all of the scores, right? So, we're not going to use the binom. Binom is for binomial. We use a different D thing, different P things, not binomial. be careful, because when I was creating these, I kept accidentally typing in binom, and then I'd be like, what? Doesn't make sense.
Give this code.
No, we'll get to that later. Okay, so if we divide all of the scores, if we subtract all the scores from the mean, and divide all those deviations by the standard deviation, we'll get a different distribution. It'll have the same shape, but it will be standardized. It will be a z distribution. So we subtract mu from each score. What will the new mean be? If we subtract the mean from each score,
M minus the process.
you think it will be 0. Does anyone else think it will be 0? Raise your hand if you think it will be 0. One person thinks it will be 0. That one person is absolutely right. Why?
Because it's
It doesn't even matter that it's symmetric.
No.
That has, I mean, you know, that defines sort of what a normal distribution is.
some of the deviation.
The sum of deviations
Zero.
is 0. So the mean of the deviations will be 0. So yeah, that's exactly right. These are just deviation scores, and we already demonstrated last class a whole bunch of times that the mean of deviation scores is just 0, right? All right, now what happens when we divide each deviation by sigma? What will the new variance be? While you're thinking about this, I'm going to reset the camera. What will the new variance be? Does anyone have an idea? The variance before was whatever the variance is, right? Now we're going to divide each deviation by the standard deviation. Does anyone have any predictions? 1. Anyone else think 1? Raise your hand. We have 2 people that have said that and 1 person with a finger up. Yes, it is 1.
Did you do it?
What?
No.
Why is it 1? Well, you can do it in your mind. So, the variance, right? It's just the sum of the squared deviation scores divided by n, right? That's what the variance is. Now, I've changed things a little bit in here, because instead of just getting the sum of the deviation scores, I'm dividing each deviation score by the standard deviation, right? So, when I'm dividing this stuff in here, I can actually take this out. If you don't remember your rules of algebra, you'll have to trust me, but if you remember your rules of algebra and how to work with this in here, well, if you take this out, that's 1 over sigma squared, right? Because you're squaring everything that's in here. So if we want to get this part out, well, we got to square it, pull it out. Well, now if that's 1 over sigma squared, but let's pull that all the way out. So put it here, right? Then we can look and see, okay, so 1 over sigma squared, or 1 over the variance, is equal to, or times this. What's this? That's just the variance. It's not sigma, it's sigma squared, right? The sum of the deviation squared divided by n. So we're taking 1 over the variance times the variance, and that's just the variance divided by the variance, which is 1. Awesome. It's 1. What would the new standard deviation be? This is even easier. This everyone should do.
1.
1. Who agrees with that? The new standard deviation is 0. All right, so raise your hands if you think the new standard deviation is 0. Not even the person who said it originally. Raise your hand if you think it's 1. One person? Okay, we need a quick review
You
here.
have to like square root.
Yes, square root. Square square root. My wife was teasing me last night because I kept saying root, square root. She's like, what, do you wear boots instead of boots? All right. So we said that sigma, or the standard deviation, is just the square root of variance, right? So square root of 1 is not 0, it's 1. Boom. Yeah. All right, this will give us the z distribution. And so here are our original scores. We subtract 100 from all of our original scores. What will the new mean be? Well, that will just shift this whole thing down to 0. Now, our original standard deviation was, what did I say it was? 15? So now we divide, and our new standard deviation will be 1. It'll be something that looks like this. It's got the same shape. It's scaled differently. I've zoomed in, right? Notice this peak is 0.4. Before, it was 0.025, right? Because we're taking all that mass and we're putting it in to a smaller space. This is the z distribution. The mean is 0 and the standard deviation is 1, same basic shape. Now, we asked what the probability of observing someone with a z greater than or equal to 2, right? So let's see how we can do this. All we need to do is just add up the mass that's at or beyond 2. That's just this part right here. Just looking at this upper table. So that is approximately equal to 0.023. I'll show you how to do this in R to calculate it exactly next class. It requires calculus. If you don't want to use R, and you actually want to solve for the true probability, you need to know calculus. But, you know, we have R. So we're going to use R instead. You can be happy that you don't have to look up values in tables. So when I was a student, I didn't use R. I used tables. Ooh, let's see what the cutoffs are and the pain in the butt. R is awesome. Okay, so let's add up the mass for z. The absolute value of z is greater than or equal to 2. This was before, just for z is greater than or equal to 2. So what will this be?
Minus 2.
We're going to be looking at both tails, right? So we're going to add in that tail too. Who wants to take a guess at what the new p-value is going to be?
Multiply by 2.
We're just going to multiply what we had before, right? How do you know that we can do that? Because this distribution is symmetric. Yes. So the probability is just twice what we had before, so it's approximately 0.046. Awesome. And you already got the answer. Okay, so now we'll talk about some common knowledge for normal distributions. These are things that a lot of statistics teachers say, know these. It's a good idea to have an idea of some of these, so that way if someone mentions something like, oh, a z-score of 1.96, you sort of know what's going on. But for most of the class, we'll be calculating probabilities using R, and we'll get the exact answers. So I'm presenting these more for convention's sake. So approximately 68.3% of the scores fall within one standard deviation of mean. This is for a normal distribution. The z distribution is a normal distribution with a mean of 0 and a standard deviation of 1. So for the normal distributions, almost 68% of the people, 68% of the scores, 68% of eggs eaten will be one standard deviation away from the mean. 2 standard deviations away from the mean. Now we're just adding up all of this area. The total area is going to equal 1, right? So the sum of all of this stuff is going to equal 1. Now if we look at the up to 2 standard deviations above and below, now we are including a bit over 95%. So what this means is if you are using an alpha of 0.05 and you get a standard deviation or a z-score of 2, well, you know that beyond that is 94.6% approximately, right? I'm sorry, is 4.6%, right? Which would be smaller than the traditional alpha of 0.05. Okay, so approximately 99.7 of the scores fall within 3 standard deviations of the mean. Now, it's interesting, in manufacturing, there's this rule, it's called the 6 sigma rule, or the 6 standard deviation rule. What they do is they try to design their industrial processes to be able to work with parts that are within 6 standard deviations of the expected size, value, whatever. So if you're making iPhones, like the little screws, they have a particular distance between the threads, right, as they're going around. So if you're using 6 sigma, what means is that if we were to measure the standard deviations of the distance between the 2 threads, that Apple's iPhones will work with threads that are 6 deviations above that or 6 deviations below that. So if something with 3 standard deviations or greater only happens basically 0.3% of the time, how much of the time do you think something greater than 6 deviations is going to occur? It's going to be very small. Very, very small. Because we're already getting very close to 0 down here. So if we went 6 away, that's boom, 4, 5, 6. That would be all the way out here. Which would be good for Apple, because then even if there's a big mistake in some part of the manufacturing process, it should still be able to work. All right, some other common knowledge. Now, instead of looking at what different standard deviations cut off, let's ask us how many standard deviations do you need to cut off a certain amount of information. So approximately 10% of the scores fall beyond 1.64 standard deviations of the mean. So this would be like a 2-tailed alpha of 0.1. 5% is over here, 5% is over there. So even if you don't know how to use R yet to calculate the probabilities, if I were to ask you on the homework that, we observed a z-score of 1.63, what should we do? Reject, fail to reject? Fail to reject. 1.63 is before 1.64. We need it to be, at least the absolute value for the 2-tailed sense, we need it to be 1.64 or greater. So, cool. If we want to cut off 5%, so 2.5% on one end, 2.5% on the other, 1.96 standard deviations will do the trick. So this is a 2-tailed alpha of 0.05. If we want to have 1% of the scores left over, so 0.005% over here, 0.005% over there, we're looking at 2.58 standard deviations from the mean. And if we want a 2-tailed alpha of 0.005, now we have 0.0025 here, and 0.0025 there, 2.81 standard deviations cuts that off. If you were to memorize any 2 of these common knowledge things, I would recommend this one. 1% falls beyond 2.58.
Why?
Some of the most common types of alphas that are used are the 0.01 and 0.05. So we got our 0.01 and this 1.96. Now notice this is 2-tailed. If you want the 1-tailed, that means you want 5% over here, right? Or over here, depending on which direction you're looking at. Now, if you were looking for a 1-tailed alpha of 0.05, do you have enough information based on what I've given you to figure out what that is? You do. Because I told you that 1.64 cuts off the most extreme 10%. That means the most extreme upper 5% and the most extreme lower 5%. So if you're looking for a one-tailed alpha of 0.05, you're looking for 1.64 or negative 1.64, depending on the directions in all the boxes. Okay. So, what if you have a z-score and you want to get the original score again? Now, this is our formula for z, right? Z is equal to the score minus the mean divided by the standard deviation. Let's say we know this. We don't know this. Can we get that?
Yes.
Yeah, it's simple. We just have to do some algebra. We need to solve for x, right? So all we do, we take the standard deviation, multiply both sides by that, right? So that goes over here, gets rid of it there. Then we're going to add the mean to both sides. So we will have x is equal to the z-score times the standard deviation plus the mean. So let's do an example. So imagine that we have a student, they got a z-score of 1.5. And the mean for the test was 54. And the standard deviation for the test was 12. What was their original score?
18 plus 66.
So we have x equals
1.5.
1.5
No, 54.
multiplied by 12 or 54. We can go back if we need to. We want to multiply by standard deviation. So that's 12. All right, plus 54. So what is 1.5 times 12? 18. Right, half of 12 is 6, so 112 plus half of 12 is 18. Plus 54 equals 72. Right? There we go. Now, it's cool. So not only can you get original scores back if you know the mean and the standard deviation in the z-score, you can also create different types of scores. So imagine that you have a teacher, and the teacher wants to curve a test. And the teacher wants the mean score to be a 75, because the mean student is supposed to have a C, according to the definition, right? So the mean's going to be 75. And they want the standard deviation to be equal to 8. That means that 3 standard deviations away, you'll have a score of 99. You can calculate that yourself. But, so we have the mean that we want, we have the deviation that we want, and we have the student's z-score. So what's the student's curved score? Score equals 1.5 by the standard deviation that we're interested in. Originally, we were interested in the original score. So we use the original standard deviation. But now we don't care about the original score. We want a curved score. So we want to use the standard deviation that we want in our curved scores. 8 plus 75. So what is this? 12 plus 75. 87. Cool. All right. You are almost never, ever going to do a test with a sample size of 1. You're going to collect 10 people, 20 people, 100 people, 200. Depending on how much power you want and other things involved. But you're almost never going to do a test with one sample. For, if you have a sample size 1, you just use the regular old Z that we covered. Now, if you have a sample size that is an n greater than 1, the formula is slightly different. Only slightly. Notice the formula is basically the same. Here, instead of the individual score, I have the mean of the scores from the sample. So this is the sample mean. So the sample mean minus the true mean. Now this, before it was just the standard deviation, right, of the standard deviation of the scores. This is actually the standard deviation of the mean of the scores. but basically it's just a standard deviation. There's a special word for this type of thing, and it's called the standard error of the mean. So if you hear someone talking about the standard error, they're probably talking about this. Now the formula, we know how to get this. This is given. So the only thing we need to know is this. The formula for that is just the standard deviation divided by the square root of n. Now here I'm going to wave my hands. Trust me for now that this works. We don't have enough time to demonstrate right now why we're dividing by the square root of n. So I'll demonstrate this later. But for right now, take my word for it. Alright, this is a standard error of the mean. Okay, so now let's do an example with a z-test. How many students, or do my students have an average name, face, IQ? So a lot of you guys did this name, face, IQ test recently. And you sent me the IQ scores that you got. Now I want to know, do you have an average, does my students have an average name, face, IQ? So the null hypothesis, I don't know why the bar didn't show up, is that the mean of my students is equal to the mean of the population. Right?
Which population?
The population mean of IQ for face name IQ scores. Alright, now which direction is this? Which tails are we interested in? It's a two-tailed test, right? Let's say we're going to use an alpha of 0.05. This is a two-tailed. Our critical values, if you go back several slides, boom. If it's less than or equal to 1.96 or greater than or equal to 1.96, then we're going to reject the null hypothesis. Now, this is important. IQ is normally distributed. If we don't know this, we can't say that these are our critical values because we don't know how the distribution looks. Okay. If you guys know about IQ, the standard mean for IQ is 100, and the standard deviation is typically 15. So we've got our mean and our standard deviation. Let's say these are my students. I had 25 students submit their scores, and the sample mean was 108. So what is the z-score? Z, we take 108 minus 100. Okay, look. 15 divided by 5, but it's divided by the square root of 25, right? So this is just 8 over 15 over 5. That's just 8 over 3. That's just 2 2/3. 2.66. What do we do? Do we fail to reject? We need to compare to the critical values, right? So this is above the mean, so we should compare to the critical value on the upper tail. So if our z-score is above or equal to that critical value, we will reject. If it's not, we'll fail to reject. We reject. Awesome. That's it. See you guys on Friday.